Dear students, welcome to Electronic Devices and Circuits Lecture 9. Today we'll study collector feedback biasing techniques. Before this we have studied fixed bias technique, emitter bias technique. In this technique we don't have an emitter resistor. Here we have an emitter resistor, a voltage divider bias where we have two base resistors. These two techniques were studied because they offer more stability versus variations in beta. Today we will study collector feedback technique. This technique is also known for being more stable versus to provide more stable bias point versus variations in beta. Today we'll perform its analysis and we'll write input and output loop equations to find out the bias point. Let's start. Here we can see that we have an RF resistor that is feedback from that is in a feedback path from the emitter side collector to the input side base. Here to write an input loop equation, we need to first identify the components that are the part of input loop. VCC, RC, this feedback resistor RF, and this resistor RE. The current through the resistor RC, we can, if we assume a current flowing through this RC, we see that at this point, at this node, the current that enters at this node splits into two parts. The current that flows through the base and the current that flows through the collector IB and IC. So this current that flows through RC must be the sum of the two according to Kirchhoff's current law. So this current has to be IB plus IC. So the current through RC is IB plus IC. The current through RF resistor is IB. And again, at this point, emitter, since we know that emitter current is the sum of the base current and collector current. So same IB plus IC flows through RE. So now we are in a position to write input loop equation straight away. VCC voltage rise minus the voltage drop through minus the voltage drop across RC. The current flowing through this resistor is IB plus IC. So IB plus IC times RE plus the voltage drop across RF. The current flowing is IB times RF. This is voltage drop, should be written as negative, minus the voltage drop across base emitter junction VBE, typically 0.7, minus IB plus IC flowing through RE. So this should be written as 0. This should be written equal to 0. So rearranging this equation, we see IC is much larger than IB. So IC plus IB is IE, which is actually beta plus 1 IB, or can be written as approximately beta IB. So this can be written as beta IB times RE. This can be replaced with beta IB. Now this equation can be used to find out the value of IB. IB is VCC minus VBE divided by beta times RE, beta times IB, beta times RE, beta times, sorry, this is RC, beta times RC plus beta times RE plus RF. So this IB is very similar to the IB we obtained in case of emitter bias and voltage divider bias, because we have a beta terms in the denominator. When we compute IC from this equation is beta times IB. This makes IC somewhat independent of beta, because this IB, if we put this IB here, we have a beta term in the numerator and in the denominator. So this IC tends to be independent of beta. So now we can write output loop equation. But before we write an equation, we must identify the components in the output loop: VCC, RC, the voltage VCE, and the resistor RE. So now we can write equation VCC minus the current flowing through RC is IB plus IE, and we have already assumed this current to be approximately equal to beta IB or IC. Minus VCE minus IB plus IC, which can be approximated as RE, is equal to 0. So now VCE can be written as VCC minus IC times RC plus RE. So in this lecture, we have studied how to find out the bias point of a collector feedback circuit. In the next lecture, we'll solve a problem related to this configuration. Thank you.